Video presented to you by Unique to Billions e-learning. Please subscribe it and press the bell icon. In this video, we are going to study Hertz Observations, Hallwach and Leonards observation, and experimental study of photoelectric effect. First, Hertz Observations. Heinrich Hertz discovered the phenomenon of photoelectric emission. During his experimental investigation on the production of electromagnetic waves, he observed that high voltage sparks across the detector loop were enhanced when the emitter plate was illuminated by ultraviolet light from an arc lamp. That is, when light falls on a metal surface, some free electrons near the metal surface absorb enough energy to overcome attractive of the positive ions in the metal surface and will escape from the surface. So, that's about the Hertz observations. Now we are going to study Hallwach and Leonard's observations. Lenard observed that when ultraviolet radiations were allowed to fall on the entire plate of an evacuated glass tube enclosing two electrodes, current flows in the circuit. As soon as the ultraviolet radiations were stopped, the current flow also stopped. This also shows that when light falls on a metal surface, the electrons absorb energy and are ejected out from the metal surface. In this observation, the ejected electrons are attracted towards the positive collector plate, and this resulting in current flow. Hallwach and Leonard studied in detail about this photocurrent for different collector plate potential and with the frequency and intensity of incident light. They observed that if the frequency of the incident light was smaller than a certain minimum value, no electrons were emitted. That is, a minimum value of frequency is required to emit an electron. This minimum value of frequency required to emit electron from a metal surface is called threshold frequency. This minimum frequency depends on the nature of the material of the emitter plate. It was also found that certain metals like zinc, cadmium, magnesium, etc. responded only to ultraviolet light having short wavelength to cause electron emission from the surface. However, some alkali metals such as lithium, sodium, potassium, cesium and rubidium were sensitive even to visible light. All these photosensitive substances emit electrons when they are illuminated by light. After the discovery of electrons, these electrons were termed as photoelectrons, and the phenomenon is called photoelectric emission. We are going to see in next section the experimental study of photoelectric effect. Experimental setup include an evacuated glass tube having photosensitive plate C and another metal plate A. There is a transparent window W through which monochromatic light from a source S can pass and falls on the metal plate C. A battery is connected to maintain the potential difference between the plates C and A that can be varied, and the polarity can be reversed by a commutator as shown in the figure. The electrons emitted from plate C are collected by the plate A. So this is electrons. This emission of electrons causes flow of electric current in the circuit. The potential difference between the emitter and collector plates is measured by a voltmeter V, whereas the resulting photocurrent flowing in the circuit is measured by a microammeter. The inputs like potential difference, intensity, and frequency of incident light can be varied accordingly. Let us mark some more in this figure. We know this is photosensitive plate. This is evacuated glass tube. This is commutator. Now we are going to study the variation of photocurrent with intensity of radiation, frequency of incident radiation, the potential difference between the plates A and C, and the nature of the material of plates C. First, we are going to study the effect of intensity of light on photocurrent. For this, collector A is maintained a positive potential with respect to emitter C, so that ejected electrons from C are attracted towards collector A. The potential and frequency are fixed and intensity of light is varied. The resulting photocurrent is measured. It is found that the photocurrent increases linearly with the intensity of incident light. The graph obtained is like this. That is, number of photoelectrons emitted per second is directly proportional to the intensity of incident radiation. Now we are going to study how the potential on plates affect the photoelectric current. That is, we need to make all other quantities fixed, that is, frequency and intensity of incident radiations are fixed, and potential on plates are varied. First, we apply a positive potential on plate A, that is an accelerating potential. In this part of the experiment, we will vary this positive potential gradually and resulting photocurrent is measured. The observation is shown in the graph here. The observation is that the photocurrent first increases with the increase in accelerating potential or positive potential, reaches a saturation point or maximum point and then remains constant. This maximum value of the photoelectric current is called saturation current. Just look into the figure. If I apply positive to plate A, the electrons emitted will be attracted towards plate A. If potential increases, all electrons will move to plate A and will be collected at plate A. That is why first it will increase and then it remains constant. So, saturation current is the case in which all the photoelectrons emitted by the emitter plate C reaches the collector plate A. In the second part of this experiment, a negative or retarding potential is applied to plate A with respect to plate C. So, we are marking here retarding potential. As the retarding potential increases, the observation is such that the photocurrent decreases rapidly and drops to 0 at a negative potential V0 on plate A. The negative potential V0 given to plate A, for which the photocurrent drops, is called stopping potential. Or cutoff potential. To understand why it happens, we are going to the experimental setup. Look at in this case, we are applying a negative or retarding potential to plate A. So, if a negative potential is given to plate A, the electrons emitted from plate C will be repelled, and only the electrons with more kinetic energy can reach the plate A. As the negative potential increases, that electrons will also repelled. So, at a stopping potential, all electrons, that is, the electrons with maximum kinetic energy, is also repelled. So, we can write the maximum kinetic energy of an emitted electron is equal to EV0. That is, at a stopping potential V0, the electron with the maximum kinetic energy is also repelled. In third part of this section of this experiment, we are going to repeat the experiment with the different intensities. Let the intensity of the first case we already done is I1, and repeat this experiment with the two more intensities I2 and I3 such that I1 is less than I2 and I2 is less than I3. The observation is as follows. The saturation current is higher for higher intensities, but stopping potential remains the same. That is, we already seen in the previous section, the emitted electrons per second is proportional to the intensity of incident radiation. So, as the intensity increases, the photocurrent increases, thus the saturation current also. But the stopping potential remains same. That means that for a given frequency of the incident radiation, the stopping potential is independent of its intensity. We already saw that the maximum kinetic energy of photoelectrons is a factor that determines the stopping potential. Therefore, the maximum kinetic energy of photoelectrons is independent of the intensity of incident radiation. Now we are going to the last section of this experiment, that is effect of frequency of incident radiation on stopping potential. In the last part of this previous section, we already studied how intensity is affecting stopping potential. In this section, we are going to repeat this experiment with the different frequencies. We are keeping intensity of this incident radiation same for this section of this experiment. Similar to the previous section of this experiment, we are going to study the change in photocurrent for different frequencies for various potential on plate A. The observation is like this. So in this case, we are going to do it for different frequencies nu1, nu2 and nu3, such that nu1 is less than nu2 and nu2 is less than nu3. We got an observation like this. This is for frequency nu1, this is for nu2 and this is for nu3. The stopping potentials are minus V01, minus V02 and minus V03 for frequencies nu1, nu2 and nu3 respectively. The observation is that the saturation current remains same for all the frequencies, but the stopping potential are different for different frequencies. Also, we can see that the stopping potential increases with the increase in frequencies. That is, stopping potential for nu1 V01 is less than stopping potential for nu2 V02 and it is less than stopping potential V03 for the frequency nu3. As the frequencies nu1 is less than nu2 and it is less than nu3. The observation tells us that the number of electrons emitted are independent of the frequencies. That is why the saturation current remains same for all the frequencies. The observation in the stopping potential tells us that as the frequency increases, the stopping potential increases. That means the maximum kinetic energy of photoelectron increases with the increase in the frequency of incident light. Now we are going to draw a graph to show the relationship between frequency of incident radiation and the corresponding stopping potential for different metals. So we are going to take stopping potential in y-axis and frequency of incident radiation in x-axis. We obtained a graph like this for two metals, metal A and metal B. This graph tells us the stopping potential varies linearly with an increase in the frequency of incident radiation. We already saw that the increase in frequency increases the stopping potential, but in this we obtain that it increases linearly. The second observation is that there exists a certain minimum cutoff frequency nu 0 for which the stopping potential is 0. That is, a minimum frequency is required to emit an electron from a photosensitive metal. This minimum or cutoff frequency nu 0 is called threshold frequency. That is, if the incident light is having a frequency less than the threshold frequency, then there will not be any photoelectric emission from that metal. The relation of maximum kinetic energy with the stopping potential and the linearity in this graph gives us an idea about the relationship between the frequency of incident radiation with the maximum kinetic energy of emitted electron. That is, the maximum kinetic energy of the photoelectrons varies linearly with the frequency of incident radiation. Here we can also understand that the photoelectric emission is an instantaneous process without any apparent time lag, even when the incident radiation is made extremely dim. Now we are going to conclude this video by summarizing the observations from this experiment. First, we saw that the photoelectric current is directly proportional to the intensity of incident light. But remember, in the last section, we saw that the frequency of incident radiation must be above the threshold frequency. So we can say, for a given photosensitive material and frequency of incident radiation that is above the threshold frequency, the photoelectric current is directly proportional to the intensity of incident light. Now we are going to see the second. For a given photosensitive material and frequency of incident radiation, saturation current is found to be proportional to the intensity of incident radiation, whereas the stopping potential is independent of its intensity. Here we saw that a minimum frequency called cutoff frequency or threshold frequency is required to emit an electron from a metal surface, below which no emission of photoelectrons takes place, and that is independent of the intensity of incident light. Also we saw that the maximum kinetic energy of photoelectrons emitted varies linearly with the frequency of the incident radiation. Here we also saw that the maximum kinetic energy of photoelectrons increases linearly with the frequency of the incident radiation, and that is also independent of its intensity. Also we can see that the threshold frequency is different for different metals. Last we saw that the photoelectric emission is an instantaneous process without any apparent time lag, and that happens even when the incident radiation is made exceedingly dim. Thank you for watching this video. Keep learning. If you are not yet subscribed to our channel, please subscribe it. Also, please like and share this video.